everybody, and welcome to our webinar on new design considerations for co-packaged optics, CPO, or onboard optics, OBO switches. So this is the 11th in a series of webinars presented by Kobo, which is the Consortium for Onboard Optics, and sponsored by DuPont's Silicon Valley Technology Innovation Center. So embedded optics at the board or module are not new, but as we go into the second half of 2022, there's a real feeling that new possibilities are opening up. So just today, Kobo is publishing a 47-page guidance document which addresses design considerations ahead for CPO and OBO switches. This paper is 47 pages long. It represents the work of 56 companies over the past 2 years. A lot of work has gone into this, thinking about where switching goes from here on out. The paper itself, by the way, is now available on the Kobo website, which is onboardoptics.org. Anybody can download it without registration, so please go ahead and do that. Our webinar today is going to last 1 hour. That paper is the basis of our discussions here today. We'll have 2 presentations. First, we'll hear from Tiger Ninomiya, who is Technology and Innovation Manager at Senko Advanced Components. Tiger is also the chair of the co-packaged working group at Kobo. And then we'll hear from Peter Johnson, who's a staff scientist at SABIC, and Peter served as the chief editor of the Kobo CPO white paper. After the 2 presentations, we should have maybe 15 or 20 minutes left over, so plenty of time for your questions. You're welcome and encouraged to use the Q&A function to submit your questions. And if you could please just say, this question is for Peter or this question is for Tiger, that would help a lot. This webinar is being recorded, and so this full broadcast will be available to share with your colleagues. The white paper, as I said, is available for download, so will be the slides from this presentation. So with that, let's get started. Tiger, the floor is all yours.
Thank you, Jim. And hello, everyone. Thank you for joining this webcast. This is Tiger Ninomiya. I'm a TNI manager at Senko, and also co-packaged optic working group chair of Kobo. So let me go through this slide deck quickly before we jump into the content summary of the white paper. Again, this is Tiger Ninomiya. I'm going through what Kobo is doing actively now, and also the future discussions, and followed by Peter Johnson, who's the chief editor of this white paper, going to summarize the contents of the white paper. So about Kobo, we have a couple of active working groups. One is co-packaged optics working group, which I'm chairing. This is started a couple of years ago to develop technical guidance and standards for CPO implementations, and especially focusing on the optical connectivity and remote laser sources. This is because while we were standardizing Kobo, we had also study groups talking about optical connectivities, which we believed that those discussions are applicable for co-packaged optics deployment. And we put the information together as a white paper for technical guidance, and you can go online onboardoptics.org, and you can find the white paper, and also you can find the presentation from today there as well. And other than this white paper, we have a couple of other projects. One is about external laser source. The other one is multi-core fiber study activity, which I'm going to explain in the following slide. So we are seeking to discuss on the topics for external laser source to identify these topics. What are the challenges and what are the probable resolutions to those challenges. So we are more than welcome for new members to contribute to study these areas. Also, we are focusing on the some of the new technologies such as multi-core fibers, which can extremely densify the fiber to chip coupling, as shown on the right-hand side as an example. But there are other challenges to deploy such a new technology. So we are currently trying to start the white paper program on the multi-core fibers as well. Another group which is active within Kobo is a multimode waveguide interconnect system, which we call MWIS. This working group is to develop technical guidance and standards for MWIS implementations. And also we are trying to specify the demo system. And potentially we make a demo unit to demonstrate this one. So topics we are currently working on is optical waveguide for PCB, and also pickup connector, and also media adapters. So this MWIS working group is looking to perform some optical modeling in the same way the PCB copper trace are. So we are trying to replace PCB copper trace with the multimode waveguide. And currently we are seeking more contributions from the EDA vendors so that we can design the toolbox for additional steps shown on the bottom. So if you're interested in participating or any more, if you need more information, you can go online on onboardoptics.org. And we have Melissa as the contact listed here. She can guide you to the right contact or explain what you need to sign up for the participating as Kobo. So please don't hesitate to contact Melissa or myself. And for MWIS, I forgot to mention, but yeah, it's chaired by Joshua Kim at Hirose. So please feel free to contact any of us for any questions, comments, or showing if you have any interest. So with that, I'm switching over to Peter. But I'd like to thank all the contributors who contributed or left comments or provided us an idea. It took 2 years, pretty longer than we expected, but finally we released the white paper. So let's jump into the summary of the white paper. Peter?
So I'm Peter Johnson. I work for SAVIC as a material scientist, developing new materials for a lot of different components that go into the connector space. And we wanted to summarize a lot about the white paper itself. So just to start, the title and abstract, I think, was sort of covered by Jim in the beginning, but really what we had a fairly, again, to the 2-year discussion was on variety of different options you could use for different switch components using either onboard or co-packaged optics, and then how that impacts everything from the faceplate to the heat source to all the fibers that would be needed both internally and externally and the management of it. And so when we look at, again, there's a summary of the table of contents. As was stated in the beginning, this is now public on the Onboard Optics website, onboardoptics.org. I won't necessarily go through the table of contents here, other than that we're going to cover sort of each one of these chapters as we walk through here on the next, I would say, dozen or so slides. So just to start off, again, when we talk about moving optics inside, we're talking about taking the optical connection, which has generally been the faceplate pluggable optic, and starting to move that on board, whether it be Kobo or actually shifting it all the way towards the ASIC itself. And once you start doing that, you start locating the optical engines along with the ASIC on a single package, which means you've moved a lot of things that were sort of previously at different locations now into one center location. And that changes a lot of different aspects of what could go on in the system. So what we did in the paper is really break it down into each subsection of what choices could you make and how would that impact various aspects of the design in the end. And so this is really going to be sort of a step-by-step walkthrough of sort of how we had our discussions was, various aspects of, well, if we start changing this, it might affect heat flow, it might affect other things. So we'll just get started with, of course, just sort of a system overview of what actually we thought changed from going, say, from pluggable to onboard to co-packaged. And really what you're doing here is you're switching a lot of the connector size and a lot of the locations of, say, heat sources and other things. So we now change how manufacturing works. We now change how the ecosystem and the knowledge base works. because we're taking serviceability and shifting the location of potential service points or even test points. We're changing how the modules would actually work because we're no longer constrained by the faceplate size in the pluggable optic box. We're also switching the package complexity because it depends on how we package and what we even choose to package into that optical engine. We can choose to have an internal or external laser source. We can choose to make the length of the fiber that comes out of that optical engine in a variety of different paths. So all of these things really do impact what goes on. And that's why, again, it's a fairly holistic approach over all the different permutations that can happen and what impacts they cause, like even down the line towards the how do I assemble it in the end and keep everything cool. So if we're just going to start, the first thing that's sort of covered in the paper is just sort of the different types of optical engines and what interfaces could be possible. This starts with sort of just having an electrical separation. So this is more like a socketed optical engine. And then the other two are actually having a soldered optical engine where you either have sort of a fiber pigtail, so your optical connection is within inside the box, or you'd have the optical connection actually within the actual optical engine itself. So you're sort of switching where the location of that connection goes. And that actually, of course, changes where all three of these change where different design considerations are needed. And this is really discussed a lot more detail in the paper, but this was sort of the overview of the three different types that we looked at and then the impacts that these have. We really did focus though on, we have fiber now, a significant amount of fiber, in fact, within the board itself. And so the next chapter really covers that midboard connection and how those fibers are routed. And when people always show this sort of standard design here, where we show an ASIC kind of sort of rotated degree in the co-packaged optics, all of these different fiber traces, most of the time people show these and they're all of these trace lines, technically, if you'd straighten them all out, are technically different lengths. We didn't necessarily think about, when you show it in a schematic, you're going to sort of leave off some of the minor details. But what really this means is that you're going to have different pigtail lengths if you directly connect it to the faceplate. You also have a risk of fiber damage because you have all these different options, all these different considerations. And you're also going to impact production yield and sort of the overall complexity of just the sheer number of components you would need. If you even limit it to 4 different types, that means you have to keep 4 different optical engines and stuff. So there are alternatives to this. And again, we had a discussion within the group itself over what types of options you could use. If we're talking about having a midboard connection, there are different varieties of things that are currently in the market. There's also ones that are currently in development. But that could simplify the process to having, say, instead of having 5 different optical engines, you now have one standard optical engine with a standardized pigtail length. And then your jumpers can be however long they need to. And again, you can potentially manage the fiber much easier in a jumper because you're not risking damage over the entire part. You're just risking damage to that jumper cable. This sort of can reduce the risk of fiber damage. It can reduce or consolidate parts. But again, we're adding additional connectors into the component system. And that kind of works out when we started to sort of overview and look at how the overall midboard connection looks once you start going from a pluggable system to the pigtail plus a jumper. Is that you start adding more and more connection points into the system. When you started with just the base pluggable, you have only that optical connector right at the faceplate within the module itself. If there's an issue, you can pull the pluggable and actually test it. Once you go to, say, just a standardized pigtail, you still have the connector at the faceplate. But once you start going to the jumper, you've added in, effectively, if it's on both sides, 2 additional connectors. This could impact loss budget. It could also impact the number of points which you could have potential points of failure due to dust or misalignment or poor connections. So some of the recommendations that are in the paper, this is not sort of full list of sort of the discussion, but again, really lower loss connectors are probably going to be needed if we start shifting towards having more and more connections within the box itself, because we've just added more and more cable points of signal loss. And we eventually are going to reach a point where, again, we're going to run into problems with just the loss budget overall. So that was sort of, I think, just a summary of sort of what goes on internally inside the box. The next thing that we talk about here is actually the external laser source. And when you think about the external laser source, this is sort of an option. You could technically internalize that into the optical engine as well, but in certain situations, there's been discussion of actually moving that off if there's sort of laser failure or things like that. you could effectively recover the optical engine because the optical engine doesn't have that laser source integrated. The three that are shown here is just, again, almost an onboard optics version where you've mounted that onto the board itself, whether it be sort of standardized here as a soldered version or as a socketed version. And what this really does is it pretty much frees up the adapter space on the faceplate. So we haven't necessarily impacted anything on the faceplate here because it's all still internalized. If we do this as, say, a pluggable pigtail, where the fiber actually, and what we define as pluggable pigtail versus blind mate is effectively whether the fiber goes outside the system or it remains inside the system. In both cases, you need to keep the faceplate area so you can actually have these pluggable modules. In the case of a pigtail, if you actually run it external to the box, you're going to be also consuming space for the connectors themselves. In the case of a blind mate, you actually have the connector within the box. There can be, of course, issues with that, and we'll get to that in the next slide, because this became a fairly large discussion. It was split out into its own ad hoc group during the course of the conversation as we built the white paper, because there's a lot of different aspects here in terms of what potentially could go on and how we would want to actually eliminate certain designs or potentially keep them all because we didn't know necessarily how the market would react. So the summary, and this is again from the paper itself, this is one of the tables, is that if you do these three different types, you have a variety of different options in terms of what you get. The onboard optic, of course, the serviceability is actually far more difficult than it would be for a pluggable system, which is exactly how it works for, say, a pluggable system right now. The pluggable modules we use for optics are much easier than something internal on board. So there's a serviceability question, but you do have eye safety considerations here, if especially we're using polarizing maintaining fiber. If they're really high-powered systems, we're going to have new technical requirements, new safety considerations, new serviceability requirements to make sure that we don't have issues in the long run. And so by actually having that blind mate connector, you could actually, eliminate lasers being directed towards the user. You could eliminate power sources until they're actually needed. When you do the pigtail version, of course, you have a much more easy system to deal with, but you do have to deal with, of course, right, the risk of actually having the laser outside of the box and in a place that you don't necessarily want it to be. In all of these cases, though, really, I think one of the things that was sort of just a key point here is that we really do have a lot of questions on this, because this is going to be an aspect where if we do believe these are going to be burning out, there is a serviceability question, there's a safety question here, and you really do have to have pristine end faces, because dust contamination on a really high-powered lens could potentially start burning and causing issues there. So there's a lot of different aspects here that needed to be worked through. I think we're still sort of in the progress of that. The version that we have in the paper is actually a good summary of where we're at today. And of course, there's always more feedback needed. And I think this is a discussion that will be going on into the future. So at this point, we've decided at least the options for all of the different things that could go on within the board itself, whether we would potentially need less faceplate. The last thing that we really have to consider is the number of connectors and what do we actually do? How could we fit all these connectors in? If you're talking about the 51.2 terabyte switch, a 32 port system needs about a 1.6 terabyte, 64 would need 800. And then if we're going to have ELS ports, you're going to need to fit those pluggable module spaces. We assumed that these would be something like the QSFP or something similar. When you do that, you start clearly recognizing that certain solutions are going to run out of room quite quickly. When we start, say, putting 64 ports of MPO connectors on, you start filling up a lot of the front space of, say, a 1U switch, because you need 64 ports and you don't necessarily have much room otherwise. If you start adding in, say, ELS ports for all of those optical modules, you've now actually had to go up to, say, like a 2RU switch just to fit everything in. So this is something that has been recognized by the industry. It's also something that I think has been coming up more and more often, and just in terms of how you would actually design these things. So the best thing that we thought we could do was actually summarize it across the table of what fiber options or fiber connector options are out there, what fibers do you get out of it? How much could you truly fit within that space? And then if we assumed either, say, 120, or not 100, 1,024 fibers or 256 fibers, what could you feasibly fit within a faceplate, and how would you have to expand it as you go on? So the top versions, again, the standard LC connector we just used as a reasonable reference. And then a lot of the new ones, including some that have been around for a fairly long time, like the MPO connector, for example. But what a lot of these show is that if you're up to 1,024 fibers, you really have to go to, say, a 2U system or 2-rack unit, like switch size. A lot of the new application spaces and a lot of the new designs that have come out in the, I would say, in the past year have all been sort of high density, high fiber connector systems where you can fit a lot more connectors on the faceplate and you fit a lot more fibers per connector. And in all those cases, we actually have a fair amount of buffer. If you look at this fibers per RU column, that the ones which are highly densified, you can fit, well above this 1,024 limit, which means that you probably have more space for other components on the front of the system. The thing about these, though, of course, is that we still have, when we show it here, we're not showing considerations for airflow. We're not showing considerations for actually just handling whether or not you could actually reach to get to each of these connectors. Wasn't necessarily the intent of this one. It was more just to show an overall space of how cluttered things can get once we start saying that you can only fit certain bandwidths through certain ports. And so one of the things that came out once we started talking about that and sort of the sheer number of connectors was what do we actually do about testing and measurement? And so if we look on the left, this is actually just a slightly colorized version of what would actually be in the IEEE standards. And what it shows is there's 4 test points. This TP2 and TP3 are usually the standardized test points. If we start moving things within the box itself, and you now have sort of a co-packaged onboard optic, we may need potential additional measurements. So you may have this what we call TP2 prime and TP3 prime, which would be almost a midboard connector measurement component as well. And these necessarily aren't in there. And again, it wasn't necessarily a statement of fact require these in the system. It was just a realization that if we have these additional connector points, we need to determine whether or not these actually become also points of standard test and measurement, and whether we even make them available, because certain designs won't necessarily have those midboard connections. They're just going to go directly to the front panel. So it was just this section was very interesting to sort of edit and have discussions with on people, because it all depends on how all of the other system parts work. So once you start assembling things, you may or may not have these. So it's really a question of, are they useful to test, and whether or not it's something that we really need in the future. And we decided to include it because this is something that's probably going to come up. Again, the midboard connector design has a fairly strong advantage in certain cases, especially on, say, supply chain and simplicity. But if we now have to add additional test points and things like that, we're going to have to work through that process through other standard agencies. The final thing that was covered was, once we've selected all of these things, how do we keep it cool? And how do we actually put it all together? So the section, which is chapter 8 in the white paper, and this is actually a very high level summary of what's in there, because there's a lot of things we could potentially do here. If we have, say, that almost kilowatt or 2 kilowatt of power that's coming out of both the ASIC and the CPOs, we have a lot of hot sources right next to each other, and we have to actually keep those cool. So we don't have too much of a space for a heat sink. If we're trying to put this into a 1RU rack, we also don't have a lot of vertical space. So we have a lot of different options that we might need to use to actually keep everything together. And this is where we just sort of show on this bottom corner, we kind of walk through different options, just sort of breaking it down to cooling by air to cooling by liquid, and then sort of some of the options that are being considered or just already in use, of course, in the air cooling space and in the liquid cooling space, just to break down what's possible and what's not possible into the systems. And what we decided to do was actually sort of give 2 different types of summaries. One is the sort of, overall properties of what you get. So air cooling, of course, heat capacity is low versus something that's liquid based. The biggest thing that came out during discussions, of course, is failure risks, in that once you start putting systems into liquid, or just selectively over, say, the ASIC for liquid, you start having, questions over catastrophic failure, leakages, things like that. And just the overall cost of the higher or more complex systems could potentially lead to more failures. So a lot of these are, of course, trade-offs that we have to make between what's the most robust solution versus what's the safest solution and what's actually the easiest solution to implement. And the versions that we're showing below are just, of course, I would say just a high-level summary of sort of the air type heating solutions. And then, of course, the liquid versions where we both discuss immersion type systems, and then more of like a cold plate type system where you're actually selectively putting it in. We also do include an actual full sort of heat analysis of if we took something like this system here and actually just tried to cool it with a cool plate, what sort of temperatures would you get to? How much of a load would you need? Whether it's actually practical to do that versus in air versus some of these other options that exist. So I think this is a really good and complete section showing off what we actually considered and sort of the overall impact of actually starting to merge everything together into a single component in the end. And so with that, I wanted to talk for about 20 to 25 minutes about this. So really in the end, we listed all of these different factors. Again, if you looked at all of the different choices we had, each one of them has say 2 to 3 to even the connector space where you have 10 plus connector types. All those different permutations are going to impact the design and space requirements for the system. So when you start selecting one thing, you can start impacting all of the other things down the chain. And really, by doing that, we had to actually look at all the different components, select them, or select options for them, and then start trying to mix and match them together. And so this was, both the optical engine, the co-packaging method, the connector selection, what we even do for the laser source and the heat management overall. And then just sort of one of the final questions is just how many true fibers will we need and what other components need to go on that faceplate. So really, I think one of the things that at least I learned from this was again, the new requirements that we need. A lot of these things have started to become available to integrate everything into a much smaller component than I think a lot of people envisioned in the past few years. But again, all of these considerations sometimes come in a vacuum where you're not looking at everything. So it's good to have this overview within the paper itself, where we cover all the different aspects just to make sure that everyone's thinking about the similar types of ideas. And where we've seen this sort of, new requirements and new adaptations to market demands has been the smaller connector designs. I would say when I went to OSC, there were a lot of different versions of new connectors that were shown off, where we're trying to, minimize the amount of faceplate area, but still allow for serviceability for handling for a lot of component design that really works without significant impact to other components. And I think that's, of course, going to be needed in the future and will continue to be innovated on. It's just something that once you start looking at other components, you do want to make sure that you're balancing those. And I think the final thing, by having done all this selection and doing some work on the heat management, you're going to have a more easy design to deal with. But of course, you're going to have a lot of different sizes and designs to do this within. So the paper itself, of course, covers all these impacts in a lot more detail than I was able to cover here. I would urge you to read it, especially the sections that you do understand and some of the ones you don't understand, because I learned a lot of different things. I generally work in the material space on more of the connector side, but some of the other discussions that were had with other companies were really illuminating to me on, those impacts do sort of cascade down into other things. So if you're interested in that sort of thing, please give it a read. And I appreciate everyone's contributions and discussions to this, because I think it made for a better white paper in the end. So with that, I'll turn it back over to Jim for the Q&A session. And I'd like to thank Tiger and Kobo for allowing me to edit the paper and get all this information out to the world. So thanks.
All right, great. Thanks, Peter, and thanks, Tiger. Certainly there's a lot of stuff in there. So it looks like we have about 25 minutes for questions and answers, and everyone in the audience, you're encouraged to send in your questions. Just use that Q&A function and let us know if it's for Peter or for Tiger or for both. That would be helpful. So as those start to come in, I'd like to kick it off with the first question to both of you, and that's kind of, if you could tell us a little bit about the intent of this paper. Was it that you're trying to just provide the options out there for each of these areas, or are you trying to give recommendations in the end, or provide more, work items for the standards groups and specifications? Yeah. So what's the intent, Tiger?
Sure. So this white paper project started to list up like those challenges and what the member companies can suggest to overcome. So this is more of the showing options so that the designer can configure from these options, I believe. However, this is not complete per se, because we still see some new technologies such as like multiple fibers or some other engine side technology to be helpful to overcome the listed challenges. So this is really technical guidance, but also we are hoping this to be open more discussions so that many more contributions can be provided to either Kobo or industry in general. So that's what I think we started this white paper project and achieved to release right now.
Yeah, and if I could just briefly add in there, for me, again, as the editor, we tried to keep everything open towards options, provided there was enough information for us to make an assessment of the design itself. We couldn't use something that had just been, of course, thought up in a lab, but things that had been at least either demonstrated or worked through were included, because really, some of this stuff is sort of in its early stages, and there's a lot of good ideas out there, and we didn't necessarily want to say, oh, this is the one case that will work, because of course, we're not sure if the trade-offs for all of these different things are acceptable. Some of the serviceability trade-offs might be, for example, others not. So we didn't necessarily want to say that, this is the solution, choose this one, because there are, questions over what the actual final customer is going to really be concerned with, because some of them might not be as concerned with certain properties as others.
Yeah, certainly some of the things are in early design work, but as you said, at OFC, there's a lot of new connectors and a lot of devices coming to market already. Do you feel like you were able to capture that in this white paper, or are things moving along even faster than what you would want, for the paper?
Well, I would say that, ideally we were targeting actually, Q1 for more finalization of the paper. But again, some of the releases at those conferences and trade shows early on during the year, we had to shift, and include some new things that were now out in the market. So we tried to keep it as up to date as possible. I would say up to, say, maybe, April, May of this year. So there's always going to be new changes, That's inevitable. But we tried to at least keep everything up to date.
All right, let's jump into some of the questions. So the first one is WDM, and did you consider WDM and how that could help with the density issues?
Let me answer that question. So, of course, within paper, we are touching base about like different type of optics, DR based and FR based. So FR is a full wavelength multiplex. So we do touch base about it, but we didn't discuss further to multiplex more channels per fiber. So that could be a good idea to continue discussions within Kobo as well. If the question was about like such as DWDM technologies to be implemented, like this is not Kobo's comment, but the challenge here to increase the number of wavelengths is, I think, if you are to use the surface coupling, the wavelengths is a little more sensitive, how the output or input angles are. So we need to consider the edge coupling most of the time, I believe. So we need to identify how many wavelengths we would like to input into one single fiber, and also surrounding challenges to be discussed. So I think this is a good area to further discuss within Kobo. Peter, do you have anything to add?
No, I think you covered that quite well.
Okay, so another question: do you have to be a member of the Kobo Consortium to get access to the white paper? No, they posted it on www.onboardoptics.org, and I think you can see it right up there in the first graphic. You don't even have to register, so you can just go ahead and download that right now. So the next one, how much heat is generated by the optical engines? And I think, Peter, that one's probably for you, and you might want to go back a few slides to number 23 or something.
Yeah, and so the version that we show here, where, again, these are estimated power versions, these were the power versions that were used within the model itself. So there's a model of the pretty much a cold plate design where we're actually trying to cool down all of these to acceptable operating temperatures, what types of requirements would be needed for the unit sizing and overall. So the versions, the numbers here, again, are just merely estimates to get I would just say, a baseline value. These can be, of course, adjusted up and down. We just wanted to walk through the process of how you would do it. So it really does depend, of course, on the design, on the customer's, like, let's say, silicon photonics solution, because at least from what I guess my experience is that some of them are much higher power, some of them are lower power. It really also depends on, right, if the external laser source is there, that power is going to be significantly lower out of those. It's because it's going to just be moved onto the board itself in some other way.
And these figures, they're generated theoretically, right? It's not lab testing yet for these.
So they were generated theoretically. The company that actually did all the work, Ragile, actually did also demo that design at OFC, and I believe they're doing it elsewhere. So if someone is interested in that, you can just let us know, and we can get you in contact with the right people to get more details on that.
Okay, and do you maybe remind us for that Ragile one, the cooling system that they used for was it air?
Yeah, no, they used a cold plate, so a liquid cooling system to actually fit it all within a 1RU switch design.
Okay, all right, great. So there's a question on, you mentioned multi-mode waveguide interconnect systems, the MWIS. Can you share a bit more detail about this? So first I would say that we actually did a webinar on it maybe 2 months ago, and that webinar is same as this format, an hour long, and it should be on the Kobo website or the Kobo YouTube channel. But Tiger, you might want to say a few words about MWIS?
Sure. Well, so like I mentioned earlier, this is the program to consider the multimode waveguide embedded in the PCB to replace the copper trace. So I believe this concept itself isn't that new. However, the industry group like Kobo is trying to do some demonstration jointly within the working group. So I think once you watch that Joshua's webinar, that you can find on Kobo's YouTube channel and our website, you should get more detailed and also more accurate information than I can give you. So I would avoid going in details within this webinar this time, unfortunately. But I can guide you to the right person if you are interested in speaking to the right contact.
Okay. So another question about testing, Peter, and this is the types of optical parameters that were subject to testing. And so I think this may be, the same theoretical versus lab testing, and in general, how much testing has been done at this point to generate the data.
So this is, I would say that within the white paper itself, most of it is theoretical. During some of the discussions, right, some of our members did, I would say, go over test cases that they've done, because again, when we wanted to summarize make a summary table where we say something is better than the other, we wanted to at least have either, right, theoretical, or in certain cases, we had actually real world data contributed by various members over what those could be. So most of what's in the paper just remains the theoretical, because some of it was, again, just people doing test designs of various connector types. And we, again, didn't necessarily have that equal, I would say, test bed for every single situation. Of course, right, the permutations here, if we try to do every single combination, would exceed, I would say, the capabilities of a wide variety of companies. So this was more using some of that data to inform us, but it's not necessarily available. And I think that some of that's also now been published through like various conferences, Photonics West and OFC, I believe. I saw some of that when I was at OFC. I at least know that. So it actually might be public. And if you need to, I think I can probably find those. And if that person wants to get in contact with me, I can at least provide that information.
Yeah, I think there probably will be a lot more publicly available testing or in the future. Maybe it's a little bit early for that at the moment. So here's a question that kind of challenges to take a step back and what is the problem this is solving that I can't do today with pluggable optics? And Peter, maybe your first slide I think had some comparisons in there, and maybe that's the place we can jump off to this wider question of, why are you doing this?
Yeah, and I would say that, again, chapter 2, which is the introduction chapter, goes into a lot more detail than, of course, just this overall summary that we have here. And again, I think at least some of the advantages that are, and again, these are either sort of statements from a variety of industry members or sort of just the, I would say, analysis of what people have done, is that by bringing the optical engines within the system, right, electrical traces and retimers are eliminated, allowing you to get to, of course, much lower, I would say, much lower, picojoule per bit sort of levels of data communication. There's that, and I think also part of it is just that, again, pluggable designs, with the size of a QSFP, right, limits the amount that you have to have, so your switch will get larger and larger, or you have to, of course, put more and more optical fibers within the pluggable system. So at a certain point, again, everything kind of tips over. The question is of course, when that happens. And that's always, I think, been the question with onboard optics and co-packaged optics. And we're seeing that more and more of this optical integration is happening at further and further points. Even in the case of, say, like consumer systems, we now have to go to optical cables for certain sorts of very long USB cables, for instance, just because you can't do it otherwise. So I think that it shifts gradually. And again, where that tipping point may come, I'm not going to claim to be the expert to know that. If I did, I would probably not be, I would probably have a much more Oracle-like, I guess, knowledge of the world. So I can't necessarily tell you when that happens. But again, there's always these fundamental limitations of what you can do with electronics. And when that happens, I can't necessarily claim to know, but I would say that the industry believes that at some point it's going to happen within, say, the next, which iteration it may be. I don't know if anyone knows that, but it seems to be coming closer and closer because I think everyone's sort of seeing where the end line is. And I know that's not a great answer. I apologize, but again, that's the best I can do for myself.
Tiger, any comments on that?
No, I think Peter covered everything.
Okay. All right. So this next question, a little bit unusual. Not quite sure where this one is going, but can you comment on over-the-air optical interconnects and any ongoing research in that area? So I guess not in fiber, but an air gap maybe between.
Sure. I think I can answer this question.
Okay.
So on probably slide 21, we had the list of connectors. And also showing the connector density or the patch panel density. So we are listing AirMT as one of the air gap style connectors, which has the much smaller footprint compared to MPO, so that you can have more ports within the same rack unit. So as you can see, this has 24 fibers per connector, then you can achieve over 3,000 fibers, where MPO 24 is less than 2,000. So we've done some mechanical analysis within this paper, not specifically about air gap technology itself, but based on that technology, we listing as one of the higher density connectivity solutions at the faceplate technology. And this air gap technology is new, but yeah, we could definitely discuss more within Kobo as needed if there's any specific applications or specific use case for the study areas.
Interesting. Yeah, thank you, Tiger. On this slide, how much of this, again, the question of theoretical versus practical, Where is the real market interest or demand in this number of fibers per 1 RU, for instance? I mean, that you could reach 3,456 fibers. That's really remarkable, but is that something that looks feasible at any time soon?
So feasible, but I don't think we need that many fibers. So we're just listing as the reference, where on the two farthest right columns listing with these connectors how much space you need to have, like 1024 fibers for DR, 256 for FR. This is showing the granularity of the different connectors, as well as potential space you can leave for other things like external laser soft ports or cooling, venting systems. So practically, people would not need this much of the dense active 1RU or the rack unit type of calculations, but I think this can be some kind of reference numbers for those who are interested in having more space or the regions in a faceplate.
Yeah, and I'd also like to point out that, again, this system here, we do show a variety of other options within the paper itself of other configurations. So again, once you're at these types of high densities, right, you can just visually see, right, and that's where it's a lot easier to just visually see the amount of faceplate area that you've opened up by using some of these higher density connectors versus, say, trying to use an MPO connector or something else.
Okay, another question. I think this one's probably coming to Peter. So 512 watts for a 25.6 terabit per second design looks like 20 picojoules per bit. Most of the silicon photonics talk is in the 1.1 to 3 picojoules per bit range. So a difference this person is noticing in the power. Why is there such a big discrepancy? Or I guess asking about the numbers, and I'm not quite sure which slide you were showing the 512 watts per.
Yeah, so he's talking
this one. Okay.
Yeah, and again, what we're doing, this was again baselining the design and how we would actually select something. This was, and of course, right, there are just certain designs with much better efficiencies. There's other designs overall that take more power. The version, again, that we chose was because a lot of the heat source will come out of out of both the ASIC and other components there. So I agree with the commenter, right, that we could have, this is where, again, I would say that it comes to a limitation of how many tests you want to do. We chose sort of a high level version because we wanted to just show the effect and actually the capability of a liquid cooled system. So again, if you reduce those numbers, what it does is effectively allow for sort of, a much, I would say, less aggressive potentially cooling system, but it doesn't necessarily reduce the impact of the design or anything like that. It just shows that these things are capable and that we can actually integrate a lot of things into the system. So yeah, those numbers, again, I think are probably like just more of the extreme worst case scenario, just to show that, how these heat effects actually impact a variety of systems in the board.
Okay, while we're on thermals, I'm going to jump ahead to a question that asks, could you tell me a contact person for the cool plate that was mentioned? I think you said that was shown in the Ragile switch. I don't know if the paper has any.
So I would say that, again, if you've downloaded the paper, I believe one of the last pages has both Tiger and myself's contact info. So please just let us know and we can get you in touch with the right person.
Okay, thank you. As of late February 22, embedded optical waveguides were being developed or discussed. Now they are mentioned only in the introduction. Are currently external connectors the preferred solution? So, Tiger, embedded waveguides.
Sure. I'm not 100% clear about this question, but yeah, I think in February probably we had the webinar about the MWIS done by Joshua, and because today it was focusing on CPO white paper, that's why we only had that information in the introduction. And I'm not super 100% sure about external connectors, what this person means, but I think that would be the good discussion points within MWIS. So I would suggest to contact Kobo, probably to Melissa, so that we can guide you to the Joshua for more detailed questions about optical waveguides project.
Thank you. Does Kobo collaborate with IEEE HIR?
So Kobo has relationships with IEEE. I'm not super clear about HIR, probably heterogeneous integration something. Not 100% sure if we are, but we are probably we are definitely open to collaborate with any other organization. So thank you for the information. I think we should be looking into this specific working group under IEEE, and definitely we should be collaborating together.
Okay, another question about pluggables. How do you see the OSFP XD pluggable connectors impacting CPO development and implementation?
Well, so this is really hard to answer as Kobo. So let me answer as wearing my Senko hat. So of course, CPO discussion started before OSFP-XD announcement last year, probably. So both of the technologies have pros and cons. Of course, per user's perspective, maybe pluggables easier to configure the switch and also serviceability. Where CPO, we only talk about switches in this white paper, but the CPO could be applicable for other applications such as machine learning, AI, and those areas as well. So depending on what you'd like to use CPO or the considered OSFP-XD, you can determine which one best fit to the application. So for the switch applications, it may delay some of the CPO deployment, but there are definitely applications that require CPO, and that's, again, I clarify that that's my personal Senko hat answer.
Okay, going back to the previous comment and question about IEEE HIR, yes, we do see a heterogeneous integration roadmap is correct, and they are putting efforts into CPO is the commentary there.
Thank you.
So that's helpful. Thank you. Is the use of VCSELs as a light source considered in this white paper?
So I would, and Tiger can jump in here if I misstate something. Again, we didn't necessarily go into that into that level because, again, we consider it more on a, we don't want to dig into the details of how someone is actually connected. Let me actually get back to the slide. I apologize. Like, we haven't necessarily stated how this, again, if we just have an optical engine within this board itself, we didn't necessarily want to go into those details of how that works. There's been separate, I know, activities from other, I would say, industry groups, right, into how you define those. And again, that wasn't necessarily required for us to actually determine all of the factors that we were looking into. So I would say that we don't necessarily say that this must be like a certain type of optical system or a certain type of thing. Even ELS, of course, is optional, right, in the definitions as we state them. So that was sort of, I would say, a bit outside of our scope because we didn't want to go and dig into how the optical engine worked. It was mainly on how we actually connect it out to the outside world and then to the faceplate itself.
Right, and Peter covered everything about white paper, so let me add something in addition to that. So again, we do have some ad hoc working group on the light source. So we can definitely bring some of the discussions about pixel or other types of laser sources within this working group, not necessarily as a white paper, but we're welcome to bringing any discussion points relative to light source or laser source. So yeah, that would be additional answers as Kobo.
Okay, yeah, there was another comment or question in the chat function, so the Q&A, that was also asking about this external laser source and how it's modulated. But I guess that's ongoing, right?
yeah, that is ongoing work.
Mm-hmm. Okay, one other question here, and this is, I think, also a theoretical one about the design of the ASICs and how you might scale this up even further. So the question is, stitching ASICs together could make room for scaling, cooling, and homogenize the length of the wire. Is that considered in CPO, especially one that can simply have ASICs with no pin stitching on the board directly? So I guess if you look at that ASIC design, what other ways could this be scaled in the future? Is that too future looking here? Or?
Yeah,
I think that's a little out of the scope of Kobo or the CPO working group. But personally, I haven't seen or heard deep discussions about such. So I would say future debating points. I would say. What do you think, Peter?
Yeah, I would say that again. That's sort of that's like far down in the iteration once all of the, once all of these questions have been like formally worked out and finalized. Only then might you. I think I understand. I think what they're asking for, and it's an interesting idea, but I struggle to think of how you, like with all the other concerns we have sometimes, if that's like, it might be far in the future for us to get to that point.
Maybe that's Kobo 2025. Yeah. Okay, so another question on reliability metrics. In this case, for the source lasers, both onboard and remote, are we ready to look for any reliability metrics at this point, or calculated guesses as to what reliability will look like? Improvements or worries?
I think it is a perpetual question that would come up, especially during the ELS subgroup. It came up quite a few times. I know that there were talks at even OFC and other places on sort of reliability testing and what would actually happen in points of failure. I think that everyone still, because it depends on how, of course, if you're making this, if you're trying to integrate it, of course, into the actual system itself, or put it in an ELS module, it depends on, of course, the type of, if it's a VCSEL, if it is actually some, like silicon photonics type laser, or there's a variety of laser types, and they all probably have different reliability data. So that was one where, again, it's a very difficult thing to summarize and capture without making that section, 10 pages long, in detriment to all the rest of the things that were discussed. So we didn't necessarily include that here. I think the ELS work group has been discussing whether or not it would be a good idea to sort of try to capture that within a separate, smaller white paper. So it is of interest, and I think that if you're interested or have some information to contribute, I'd urge you to get in touch with people, and we can get you to the right people to share your knowledge.
Yeah, I think that will be a very critical question going forward. Of course, it has to be reliable, and you'll have to measure it to know. So we're almost at the top of the hour. I wanted to give maybe the last question here to both of you, and that can give you a chance to give some final thoughts. I know you've just published this very long white paper, and there's a time to celebrate, I guess, and to be happy of the work that's been accomplished. But what comes next? Tiger?
Sure. So as I mentioned in the beginning, we are open to discuss more about external laser source, which we heard lots of questions about it. So great that we are focusing on external laser source as one of the ongoing topics. Also, we are in discussion of the future technologies such as multi-core fibers, how we can leverage the density we can achieve with that, associated with some other surrounding concerns and also the use cases. So these are two topics we are discussing ongoing. Also, we're open to discuss furthermore, such as operational or the process-related topics such as temperature, handling more in depth of the installation, as well as testing at the field. So definitely we are not completing everything about co-packaged optics yet. So more than welcome to hear more interesting topics to discuss within this working group. And the soon to be, you'll be seeing some updates on the some of the white papers from these subgroups we have.
All right, great. And Peter, any closing thoughts?
I think I just sort of mirror what Tiger said in that having gone through this, right, we tried to keep this at a higher level, but I would say every single section, there was enough interest that you could have probably made that and split it off into another, say, 50-page white paper. So I think it's really just it's a question of, right, where's the biggest need and what's the most urgent thing to actually try to resolve so we can get a better handle on how to integrate all these components in the future. And have all that data so we can narrow these choices down from, say, having 3 to 4 options down to maybe 1 or 2, so we can start narrowing in on the best option to actually make this sort of the standard in the future.
Excellent. Well, with that, we're at the top of the hour. Again, I'd recommend to everybody watching this, please go ahead and download the white paper. Their contact information is provided in there. So if you have follow-up questions, definitely you're welcome to do so. Thank you, Tiger. Thank you, Peter, for sharing your thoughts today on this. That's been great. And I'd also like to thank Consortium for Onboard Optics and, of course, our sponsor, DuPont Silicon Valley Technology Center. So thank you, everybody, and have a great day.